Assalamu alaikum. Welcome back to our series of lectures. Today we are going to talk about active filters. It's assumed that you already studied the frequency response and you already know the low pass, high pass, band reject filters under RLC circuit analysis. Before we go into the analysis of high pass, low pass, band pass, active filters, what's a filter? The definition of a low pass filter, it will allow a certain low frequency to pass and reject the high frequency. High pass filter will allow high frequency to pass, reject the low frequency. Band pass will allow a band of frequency, for example, between F1 and F2, the frequency between frequency 1 frequency 2 to pass and reject the outside. Band reject frequency. You have a frequency, it will reject a certain section of frequency and allow the outer to pass. During our session for active filters, we are going to use op-amp. Let's start with low pass filter. What's a low pass filter? Let's get two different colors. I want to analyze this circuit. Negative, positive. And here I have a resistor R1. In here I have R2 and I have a capacitor. See, this is the input, that's the output. Analyzing this circuit, it will give me that the output is equal to minus RF, Rin, or minus ZF, Zin, time Vin. So straight away, I know from my op-amp chapter, I know that H of S is equal to minus ZF over Zin. That's an active filter. To analyze this circuit, what's a ZF? ZF is equal to 1 over SC for the capacitor parallel with R2, which is equal to R2 multiplied by 1 over SC divided by R2 plus 1 over SC, which is equal to R2 divided by 1 plus R2 SC. Zi in this case will be equal to R1. This is R1. So what I did now is I analyzed the circuit. H of S is equal to V output over V input. I know from the op-amp that the output voltage is related to the Z feedback and Z input. That's how I put it. So now let's analyze what's H of S. This, it's equal to ZF. So now if I am going to analyze H of S, H of S will be equal to minus, put it in a bracket, ZF, which is R2 over 1 plus R2 SS divided by R1. Remember, this divided by R1 is like I'm having R1 over 1. Replace it. So now I can take on the outside, I can take H of S on the outside. It's equal to minus R2 over R1. I take out, multiply by 1 over 1 plus R2 SC. Do you remember from the chapter of the RL and RC and RLC chapters? I need to take this S, put it into S on its own. So what I do is now, I can say it's equal to minus R2 over R1 multiplied by 1 over, I will take R2C outside, 1 over R2C plus S. Is that all clear? How did this transition happen? Now, I can straight away, based on this system in here, based on this system, I can go up and start in here, and I can see that h of s is equal to minus R2 over R1 multiplied by 1 over R2C divided by S plus 1 over R2C. This is known to me now as a K. This is known to me now as omega C. Remember, when S is 0, the frequency is 0. When the frequency is 0, I have this is maximum. When the frequency goes to infinite, this goes to 0. That's why I know it's a low pass filter. And this is now my equation. Is that clear? Let's take a moment to digest this information because before I delete it. And I put the final answer. So now I have h of s. The answer of h of s will be minus k omega c divided by s plus omega c. K is defined by R2 over R1, omega c divided by 1 over R2C. Now, let's do an example. Let's do an example. This is now my, let's do an example. The question is, I need to design low pass filter. I need to design an active low pass filter using, I have only a resistor, R1, it's equal to 1 ohm. And I need to design a gain, I need to have a gain, it's equal to 10. The gain is equal to 10, and I need the cutoff frequency. I need to have a cutoff of 10 radians per second. So I need to have a cutoff of 10 radians per second. I need to have a gain of 10. I need to design an active. Low pass filter. Okay. What I learned, perfect. Gain, guys, the gain, K, it's equal to 10. It's equal, what I learned, it's equal to R2 over R1. Is that correct? R2 over R1. And now, also, omega C, what I learned from omega C, 1 over R2C. 1 over R2 times C. Perfect. This will give me R2, it's equal to 10 ohm, because R1 is given to be 1. From this one, I have R2, it's equal to 1 over omega C times C. Correct? Which is also gives me C, it's equal to 1 over omega C R2. So C now, it's equal to the capacitor, it's equal to 1 divided by 10 plus 10, it's equal to 0.01 farad. To sketch a circuit, this is 1 ohm, this 10 ohm, this 0.01 farad. Is that clear now? Is that clear how I design an active low pass filter? This is an active low pass filter. Take 1 minute or 1 moment to digest this information before we move on to high pass filters. You've seen the circuit on the board. All I did is I took the capacitor to be parallel with R2 and I put it in series with R1. I want you now to tell me what H of S. I want you now to tell me what H of S equal to using circuit analysis. Okay, great, perfect. Let's start analyzing the system. Still, H of S, it's equal minus ZF over ZI. ZF in this case is 2, is R2 minus, divided by ZI is R1 plus 1 over SC. Great, which is equal to minus, let's do step by step, R2 divided by R1 SC plus 1 divided by SC. Okay, which is equal to R2 SC divided by R1 SC plus 1. Can you all see this? This is a system. Now, remember, I want to have it at the bottom in a form of S plus something. If you remember from the frequency response chapter, I need to take it into a form that will help me to determine the high pass, low pass filter. So I need to have it in a form either S divided by S plus omega C or omega C divided by S plus omega C, or this type of form. So let's do some more analysis. So I have on top, I should have R2C multiplied by S. At the bottom, this is multiplied by S. At the bottom, I should have R1C S plus 1 over R1C. I haven't done much. All I did is I said R2C multiplied by S, and at the bottom I took R1C on the outside. It's give me R2C divided by R1C, it's equal to S divided by S plus 1 over R1C. Guys, sorry, this is multiply. This and this will go. The answer will be, so don't forget the minus, guys. Everything has to have a minus. Minus R1 over R2 over R1 multiplied by S divided by S plus 1 over R1C. This is K, this is omega C. So now the answer will be equal to, for this system in here, it's minus K S over S plus omega C. K, it's equal to R2 over R1, omega C 1 over R1C. Is that clear? This system will provide me, this system provided me with, hey look, it's a high pass filter. Recall the information that we learned in the frequency response circuit. This is a high pass filter. Let's do an example. Let's do an example. By the way, what we did now is first order active filters. First order active filters, guys. Now, let's design a high pass filter to meet the following. I need you guys to design high pass filter to meet the following conditions. Gain of 100. So the gain must be 100. Cutoff frequency, the cutoff frequency is 1000 hertz. Is 1000 hertz. And I only have one resistor. Capacitor is 1 microfarad. So I have plenty of resistors. I have an op-amp. I need to design an active filter. Gain of 100, high pass filter, gain of 100. The cutoff frequency is 1000 hertz. And I only have one capacitor available, 1 microfarad. I don't have a luxury of multiple value of capacitors. I have only one. So what do I do now is I follow what I learned. Perfect. This system will give me omega c, it's equal to 2 pi fc. I multiply the system and omega c will equal to 6,283. 6,283.2 radians per second. And then, what do I have now? I have omega c, it's equal to, so let's write it down here. Omega c, it's equal to 2 pi fc, which is equal to 1 over r1c. Look, I know what's a pi, I know what's fc, I know what's a c, 1 microfarad. So now this, it gives me r1. If you do the calculation, you will end up with r1, it's equal to 159.15 ohm. Perfect. Gain, K, it's equal to R2 over R1. So therefore, R2 is equal to K R1. K is 100, it's equal to 1000. So I have 15,915 is, so the system for R1 is found to be 159.15 ohm. This 10 to the minus 6 farad, and this will be equal to 15,915 ohm. Is that clear? How I designed an active high pass filter? All I need is I knew the capacitor value, and then I knew the gain and cutoff frequency. If I have the luxury of multiple capacitors and multiple resistance available in my hand, what can I do is I don't need the capacitor, because I can then design the value of my capacitor by knowing, all I need to know is what's the gain and what's the cutoff frequency. Where can I use this system? Radio frequency. I can get rid of all the low frequency if I don't want them. Now, I hope that's clear. Let's now go and determine the design element required for band pass and band reject for an active system. Okay, let's look now. What's a band pass filter? To design an active band pass filter, what I do is I need 3 different elements. Element number 1, I need low pass filter, active low pass filter, gain of it is 1. I need high pass filter, an active high pass filter, gain of 1. And then I need a normal op-amp for a gain purpose. So what I do is, it's also, I want you to, so this is my system. Look guys, this is my system. This is my band pass filter. This is my high pass filter. So this is low pass filter. And then I have, this is my high pass filter. So what happens is I allow a certain system will be rejected. That's how the concept behind it. So let's now set, I need for the band pass filter, I need to set two elements. I need omega C1 and I need omega C2. Omega C1 is where this is where the band pass filter. That's where the band pass filter exists. Guys, I want you to memorize this very carefully. For a broadband filter, the broadband filter requires the followings. For the broadband filter, I need omega C2 over omega C1 equal to 2. I need this relationship for a broadband filter. So how can I design the system? Look. How can I design my system? In here, goes into here. And at the end, I have this must be, this is R low, C low, this is RH, CH, RH, this is RI, and this is RF. What I've done now is, as I said before, I need a low pass filter, then a high pass filter, and then a gain if it's required. Low pass filter in here, this output in here, this I have, remember this? It's equal to omega C. This is 2 because remember it's on the outside, divided by S omega C2 minus. K is 1 because they must have the same resistors, so K is 1. Then this will have S minus S divided by S plus omega C1 cut off 1 because remember it's for the band pass, and at the end in here I have minus RF over RI for the gain, and this is my H of S. That's my H of S. That's my H of S. Now, under the condition where omega C2 is very big compared to omega C1, then I can go ahead now and define my center frequency omega 0 and my bandwidth and the bandwidth beta. Is that clear how I design the system? And still I have omega 0. I can have omega 0, it's in relation to omega C1, omega C2, and I have the bandwidth also is between omega C1 and omega C2. Is that clear? Is that clear? If I ask you now to design, for example, to design a band pass filter, that have cutoff frequency that will only allow the frequency to pass between F1 it's equal to 100 Hertz, F2 it's equal to, for example, 1 million Hertz. For example, figure of speech. These two, to design a system, to design a system like this, and you have like before, we had only only one type of capacitor. It's equal to one, for example, microfarad. I have only one capacitor available. I have my choice of a resistance and this one. Do you want to have a gain? It's up to you. I want to, for the sake of this program, for this example, I want to use a gain of 1. So I want to use, the system will have a gain of 1. Let's design the system. F1 for the frequency 100 Hertz, it will give me, remember the 100 Hertz, it's related to this one, which is related to the band pass filter. Remember this omega C1, 1 over, remember H, CH. Remember this from the high pass filter, it's equal to 1 over R1C. The second one, this one here, this one, it's 1 over R2C or R low C, because now I call them R low and R high. CH. So this provides me this 100 Hertz. Now I have omega C1, I have omega C1, it's equal to 2 pi F cutoff 1, which is equal to 1 over RH CH. Omega C2, it's equal to 2 pi F C2, it's equal to 1 over R low C low. Look, pay attention. This is this one. This is this one. This is known. These both, you have only the choice of 1 microfarad. So for this one, I can calculate RH, I calculate R low, and I can plug in all the numbers. For the gain, I use these two exactly the same, because I need the gain of 1. Is that clear? The concept. Is that clear? The concept of band pass filter using active component. Is that clear? One more item before we finish. I want to introduce to you the band reject filter. The band reject filter, you use exactly also low pass, high pass, and then a amplifier for a gain. However, at the low pass and the band pass, the low pass and the high pass will be put into, this is my system, low pass filter, high pass filter. These two will go into a so what I've done now is I need to have low pass filter, high pass filter, and then a summation amplifier. So let's now put this together of what I learned. I need then I need another negative, positive. This is R low, C low, RH, CH, RH. These two output will go RI, RI, RF. and this is where your input. So what will happen now is the top one will allow the top one. See the top one now. If I draw the circuit, if I draw my circuit, the top one will allow for this to pass. So this is my low pass filter. The second one, the second filter, the volt will allow this to pass. This high pass filter, and this area will be rejected. They will go to a summation amplifier where I can sum them together and have a gain of minus RF over RI. This is known as a band reject filter, active band reject filter. I hope that's clear. I know it was a rushed session, but we assumed that you already know the characteristic of a frequency response based on the previous chapters. I hope that's clear, and I really hope you gain some information how to design an active filters, if it was low pass, high pass, band pass, or band reject. I hope you all stay safe, and we'll see you during our next lectures. Assalamu alaikum.